Zeal Education Society, redefining excellence.
Hello, good morning to everyone. Myself Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. In this video lecture, we are going to learn the effect of excitation on armature current and power factor of synchronous motor with constant mechanical load on it. That means input power to the motor remains same. As the output is same, input power also remains same. And what is the effect of excitation system on the armature current and power factor? Look at the figure 1. Here the voltage is taken as a reference vectors for all the phasors. Voltage is taken as a reference phasor, and it has been observed that locus of the armature current is a straight line shown by the dotted lines. Locus of armature current is a straight line shown by the dotted line. Okay. Now in a case 1 where the excitation is 100% and back EMF equal to Vph. Motor works on lagging power factor and magnitude of the current is little bit less, lagging the voltage by a small angle. Now when the excitation becomes less than the 100%, it is known as under excitation and motor works on a lagging power factor. See the case 2. Motor works on lagging power factor and the back EMF generated is less than the V, the per phase voltage. Now in this case, the magnitude of the current is large and lagging the voltage by a large angle. However, the active component of current, that is OA equal to I cos phi, will remain same in both the cases, case A and B. Now if you observe the figure number C, here the excitation is more than 100% and we can say it is a overexcited case. In this case also, the current is leading the voltage by an angle phi and the magnitude of the current is large and the EB is greater than phi. Now at a certain excitation, in figure D, it has been shown that at a certain excitation, the armature current is in phase with the voltage and its magnitude of the current is minimum, that is OA. Magnitude of the current is OA and minimum, and in this case the EB is slightly greater than phi. Now we can conclude, summarize these things. See here, we can summarize it like this. It has been observed that when the excitation is increased, the armature current increases. Armature current has a large value, large magnitude at a low excitation and at a higher excitation. And for a certain excitation, the magnitude of armature current is minimum. Thus, if we plot a graph of armature current on the y-axis and field current on x-axis, the graph will be, a curve will be like a phi curve, English alphabet phi, and hence it is known as phi curve. Further, it has been observed that when the excitation is low, power factor is lagging and magnitude of the armature current is large. At a certain excitation, the armature current becomes minimum. Armature current becomes minimum. And if the excitation is further increased, that is overexcited case, motor works on leading power factor and once again the armature current, magnitude of armature current becomes large. Thus, if we plot a graph of armature current on y-axis versus field current on x-axis, you will get a curve like a English alphabet phi and hence the name. Now here the figure shows the family of phi curves. Family of phi curves, particularly at no load, half load and full load, and at a certain excitation, every case the armature current becomes minimum. At a no load, armature current becomes minimum at a certain excitation. Now for a half load, the armature current becomes minimum with increased excitation. Further, at full load, the armature current becomes minimum and its magnitude is large as compared to previous two cases, and that occurs at a different excitation, means at a higher excitation. Similarly, if we plot a graph of power factor on y-axis against the field current on x-axis, you will get the family of curves at a no load, half load and full load. And the curve looks like a inverted V, and hence it is known as inverse V curve or a power factor curve. Now if you observe carefully, at no load, the power factor becomes minimum at a less excitation. If the load on the motor is further increased, say half load, in order to get the unity power factor, we need to increase the excitation. Further, when the load on the machine is increased and it becomes full load, the power factor becomes unity at a larger field current. So that's why we are getting these 3 points, 1, 2, 3 respectively, for a no load, half load and full load. Okay. So this is about the phi curve of the synchronous motor. Okay. So at a low excitation, once again, the power factor is lagging. At a higher excitation, power factor is leading. Both at a lagging and leading power factor, magnitude of armature current is large. And at a certain excitation, the armature current becomes minimum, that is at a unity power factor. So the armature current becomes minimum at a unity power factor. So in this way, we have finished the phi curve and inverse phi curve of a synchronous motor. Now let us see why the synchronous motor is called as a synchronous generator or a synchronous condenser. Why synchronous motor is called as a synchronous condenser? When the synchronous motor is overexcited, it works on a leading power factor at no load. During this overexcited case, it draws a leading current. It draws the current leading to voltage like a capacitor, like a condenser, and hence the name synchronous condenser. Now, in such a case, the synchronous motor at no load during overexcited case can be used to improve the power factor or power factor correction in the power system. It is also used as a reactive power control. We can say it is a cheap and flexible source for reactive power control ranging from simply by changing the excitation. It can inject the reactive power at a lagging power factor under excited case, whereas it can inject the reactive power during the peak hours when it works on a leading power factor, that is overexcited case, whereas it can absorb the reactive power during off-peak hours while the synchronous motor is running under excitation at a lagging power factor. So, in other words, we can say the synchronous motor is used as a power factor correcting device or a phase advancer, and it is a very flexible source in order to control the reactive power during the peak hours as well as off-peak hours.